In this chapter, we're going to be using trigonometric identities to evaluate, verify, and solve trigonometric equations. So these are some of the identities that we discussed last chapter. And if you don't already have these jotted down or memorized, go ahead and pause the video right now and write these down. And because we're going to be using these throughout this lesson and throughout various lessons in this chapter. So definitely make sure that you know these fundamental trigonometric identities. And I've already discussed them in previous lessons, so I won't go through driving them right now, but definitely make sure that you are familiar with these. All right, so let's go through a couple of problems where we are going to be using some of these identities to do various types of tasks, whether it's evaluating functions. So let's start with something like that. And if you're looking at this should look very familiar. Because this is a problem that's pretty similar to what we did in chapter 4 or in the previous chapter. But we're going to use some of the identities to find the values of all 6 trig functions given this information here. Before I proceed, I want to make sure that we understand what an identity is before we start using it. An identity that is an equation that is true for all values of the variable. So let me give you an example of something that is not an identity. Something like x plus 1 is equal to 2. This would not be an identity because this equation is only true when x is equal to 1. So this is not an identity. However, if I said something like tangent of x is equal to sine of x over cosine of x, no matter what angle x might be, this equation is always going to be true. This is known as the quotient identity. Tangent of some angle is always equivalent to the sine of that angle divided by cosine of that angle. Okay, so we learned a couple of identities last chapter. We're now going to start using them. So let's start with this problem here. So we're told that the cosecant of negative x is equal to negative 5, and cosine of x is equal to root 24 over 5. We know that when cosine gives us a positive output, we could be in quadrant 1 or 4. But when we take that into account with what's given in the first part, we're told that the cosecant of negative x is equal to negative 5. Well, the fact that I have a negative argument here, we know that the cosecant of negative x is equal to negative cosecant of x. And again, we're told that cosecant of negative x is equal to negative 5. So if that is the case, then we know that the cosecant of x is equal to positive 5, which if you want to, you could also then write that the sine of x is equal to 1 over 5, because sine is the reciprocal of cosecant. So now that we know sine is positive and cosine is also positive, this tells us we have to be in quadrant 1. So I could draw an appropriate triangle here, and I could say that, okay, well, cosine of some angle x is adjacent over the hypotenuse, and this works out also with us understanding that sine of x is, sine of x in this case, I mixed these around, didn't I? So I apologize. Adjacent is root 24, and hypotenuse is 5. Sorry, it's been a long day. All right, so sine of x is equal to 1 over 5. So from here, once we have this triangle, we really know all of it. We already know what sine of x is. We already know what cosine of x is. We can say that the tangent of x is equal to 1 over root 24, which rationalizes root 24 over 24. Cotangent of x is simply equal to root 24. And we can then say, and which we probably should simplify to 2 root 6. This similarly then 2 root 6 over 24 would be equal to root 6 over 12. And we can then say something like the secant of x, which is hypotenuse over adjacent, is 5 over root 24, which is 5 root 24 over 24. Okay, which we can then simplify as well. This would also be then 5, this would give us, what is that? 10 root 6 over 24, which we can then simplify. This would be 5 over 12, okay? So we know the drill. We've done these problems before, and I just wanted to highlight that we are actually using identities when we're doing problems such as this. Let's switch gears. Now let's talk about simplifying, okay? This is going to be something that we want to be pretty comfortable doing because we're going to be verifying in the next lesson. And a really integral skill in this is being able to simplify trigonometric expressions. So let's do a couple of practice problems where we just want to rewrite some expressions into a single trigonometric function using the identities that we know. To start off, we know that the secant of x, in this case, is 1 over cosine of x. And cotangent of x is equal to cosine of x over the sine of x. And this allows us to pretty easily divide out our cosine x. So this is equal to 1 over the sine of x, which is equal to cosecant of x. There's our simplification. Okay? All right, well, let's try another one. Let's try something like this. Well, this one here, I could say the tangent squared theta is equal to sine squared theta over cosine squared theta. And all of this is 1 over cosine squared theta. And I can rewrite this then as sine squared theta over cosine squared theta times the reciprocal of our denominator, which then just gives us sine squared theta. Okay? Alternatively, I could have also done this. Tangent squared theta using our Pythagorean identities is equal to secant squared theta minus 1 over secant squared theta. And if I split this up into two fractions, I then have secant squared theta over itself minus 1 over secant squared theta. And this gives me 1 minus cosine squared theta, which again, using another Pythagorean identity, we can then say is equal to sine squared theta. Same thing. Okay? So I'm highlighting here that there are various ways to get to the same result, right? It depends on which trigonometric identities you use. Okay? All right, let's try another one. Let's try something like this here. So for something like this, I notice that I have a sine x in both of my terms. So I can actually factor that out, and I'm left with cosine squared x minus 1. And this is equal to negative sine squared x, which would make this negative sine cubed x. I'm just writing the equal signs to show that these are all equivalent to one another. All right, let's try a few more. Let's try something that involves, you guessed it, a cofunction. We know that the cotangent of pi over 2 minus theta is tangent theta, and we multiply that by cosine theta. And tangent can be rewritten as sine over cosine times cosine of theta. And there we go, that we just have sine of theta. Okay? All right, so take a moment right now. You can also try these two problems here and check your solutions with what I have Schoology, but we'll do more simplifying in just a moment. Let's slightly switch gears right now and talk about factoring. And this is going to be somewhat counterintuitive. It's going to go kind of against our instinct, but I want us to just practice factoring. Not worried about kind of simplifying, but just make sure that we're comfortable just factoring here. And I've written out a couple of different things to think about as we are factoring, but the main thing that I want to emphasize here is I want you to think about each trigonometric function almost as if it's a variable. For example, if I let a be equal to the sine of x and b equal to the cosine of x in this very first example, then this is no different than trying to factor something like this, which we could say, all right, a is a common factor in each, so I have 1 plus 2b. Now, you don't actually have to write any of that out, but if it helps at all, you could think of factoring out the sine x, and you have 1 plus 2 cosine x here, right? Now, again, you don't have to write out the variables or redefine anything, but I just want you to see that structure. And don't worry too much as you work through these problems about trying to simplify. Just focus on getting comfortable factoring using trigonometric functions. So let me just do one more. Try something like number 4 here. Or actually, maybe I'll do a few more. Secant squared theta minus 1. Hopefully we see that this is just a difference of squares. This is, think of x squared minus 1. It's just a difference of squares where this is x plus 1 times x minus 1. So this would be secant theta plus 1 times secant theta minus 1. Okay? Let's try another one here. Let's try something like number 5. Okay? So number 5 here. Well, at first glance, this is kind of like having y squared minus x minus 3. We don't have the same variable here. But fortunately for us, we actually have some trigonometric identities we can lean on. We know that cosecant squared x is equal to 1 plus cotangent squared x. So that's the case. We have cotangent squared x minus cotangent x. Combine 1 and negative 3, that's negative 2. Now this allows us to factor pretty easily. Okay. What about something like this here, number 6? Again, hopefully we see the structure. This is equivalent to thinking of the following polynomial. So we could just factor this just like it's a regular trinomial. This would be sine squared x minus 1 times another sine squared x minus 1. And each of these can be factored even further as well. This would be sine x plus 1 times sine x minus 1, since it's a difference of squares. And since we just have another set of sine x plus 1, sine x minus 1, I'm just going to square each of these. Okay? All right, let me do one more. For this one, think about how can I factor using grouping? Well, you can see that this would be one group, and this would be another group. Well, secant cubed x minus secant squared x, we could factor out a secant squared x, and we're left with secant x minus 1. From here, if I factor out a negative 1, I've got negative, oops, not negative, this is already just positive, secant x minus 1. And if I factor that out, I've got secant x minus 1 times secant squared x minus 1. And again, we can factor this further. This would be secant x plus 1 times secant x minus 1. And if we leave it in expanded form, it's that. Or you could just make that a quadratic there as well. All right. Okay. Let's continue on with a little bit more simplifying. Go ahead and pause the video and see if you can work through these. Using some identities, we can say that this is equivalent to sine of t plus cosine of t over sine t times another cosine of t. And you'll notice that in order for me to really simplify this further, I'm going to want to write this all using the same variable. That is to say, multiply this by sine t over sine t. So now we have sine squared t plus cosine squared t all over sine t. And what is sine squared t plus cosine squared t? The Pythagorean identity says that that is 1, which allows us to write this as cosecant of t. All right, it's a pretty similar deal for number 2 here. So for number 2, I'm going to say 1 over sine of t minus cosine of t times cosine of t over sine t. And you can see it's a pretty similar problem. I'm going to multiply this entire fraction here by sine t over sine t. Actually, they already have the same denominator. So we can just jump straight to 1 minus cosine squared t over sine t. And using the Pythagorean identity, I know that sine squared t in the numerator over sine t is equal to sine of t. Okay? All right. Let's try another one here. Let's try something like number 3. And at first glance, this looks a little gnarly, but know that if I want to rewrite this as a single identity, I'm going to need to make, or a single trig function, excuse me, I want to make sure that I have the same denominator, right? So my least common denominator is going to be sine x cosine x. So I'm going to multiply this by sine x here, sine x down here, which means I'm going to over on this side. Let me actually just move this 3 out of the way so I don't get too confused. Which means I'm going to then go cosine of x over cosine of x. And this allows me to distribute that cosine of x to all the terms on the inside. So cosine x, sine x, plus cosine squared x, plus, and I'm also going to do the same thing in the numerator on the other side, sine squared x minus cosine x, sine x, all of this over cosine x, sine x. And although this looks like it's a lot, there's actually a lot that we can simplify here. We know that this is equal to 1. And we also know that we've got a cosine x sine x and its conjugate right there. So this simplifies really nicely to just 1 over cosine x sine x, which then I can rewrite as 1 over cosine x times 1 over sine x. And there's secant x and cosecant x. Okay. All right. Now, I want to actually switch gears and talk a little bit about verifying. We will do that much more in the next lesson, but hopefully, this lesson has been helpful in using identities to rewrite, to factor, and to simplify trigonometric expressions.